So as we turn our attention to finding the equations of these different tangent lines, it'll become important for us to actually remember how we write the equation of a line in a bunch of different forms. So that way we can understand what it is that we would need to actually acquire to write this equation of a tangent line down. Now you might recall that there were two different kind of forms that we used when we wrote equations of lines in algebra classes in the past. So there was this slope-intercept form, which actually required two different things. It required us to have a slope, which was represented by m, and of course an intercept, which was represented by b, the y-intercept specifically. Notice that that's where the name slope-intercept form actually comes from. They're the two things that you need. So you can also see here that we had another form, one that was told to us a long time ago, but chances are we've forgotten about. It was point slope form. Now, point slope form, you can probably imagine what it requires that we need in order to write its equation. We need a point and a slope. What it actually comes from is the idea that slope itself, remember, was given by doing a change in y over a change in x. And actually, if you were to just take this bottom quantity and multiply it to the other side, you would end up with something that looks like this. And this right here is actually the the point slope form. Notice it just needs a point, x1 comma y1, and a slope, and you can construct the equation of a line. You can obviously do some algebraic manipulations to rewrite this into a form of y equals mx plus b. However, it's going to be primarily important in this class to understand how to use point slope form. Many of you might ignore this recommendation. I think that's a really bad move. I know many of you are probably way more familiar with slope-intercept form, and that's totally fine. But things will be so much faster. Tangent line equations will be so much easier to construct if we are able to actually use point slope form. So I really encourage you to focus on how I'm using that in these videos, because I believe it's going to save you time in the long run. I don't want you to have to do more work than necessary. So let's take a look here at example number 2 to kind of see how exactly I can use maybe the concept start to be able to create equations of some tangent lines. All right. So let's see. Let's consider a curve, a simple curve, given by y equals x squared. We know this curve. We love this curve. It's our good old parabola. Vertex sitting right at the origin, maybe looking something like this, right? This is our y equals x squared. Now we want to find the line that is secant to the curve. Okay, all right, so we're going to start by finding a secant line to the curve. And here are the 2 points that it's going to go through. It's going to go through the point 1, comma 1, let's say that's right here, and 1/2 comma, or 1.5 comma 2.25. So let's just say that's right there, okay? So if there's a line that connects these two, maybe it goes like this. So we could probably tell about this line, it's probably going to have maybe a negative y-intercept, it's probably going to have a positive slope, but finding this would be really simple. Right? We know that if I wanted to use point slope form to create the equation of the line, I would need slope, and I already have 2 points. I got more points than I need. So let's just go ahead and calculate slope. So first I'll say that we calculate that our slope is going to be, let's see, I'll do y minus the y over x minus the other x value. So this is going to give me 1.25 over 0.5. And if you were to actually go ahead and crunch that out in the calculator, you'd actually be able to see this is a pretty simple value here. This is actually just going to be 5 halves. It's 2.5. Notice you need 2.5 0.5s to end up making up a 1.25. So that's kind of where that's coming from. So once I have this, notice that using point slope form is easy. So I can say here the equation of the secant line is, well, y minus a y coordinate from one of these points. I can really choose either point that I want. I'm going to choose the point P because it looks like it's got easier values to work with. And then that should be equal to my slope times x minus the same the x coordinate that comes out of the same point that I originally picked. So here it is. There's the equation of my line. Now, of course, if I wanted to, I could simplify that down a little bit to get that to be in slope-intercept form. I could distribute my 5 halves. So I would get 5 halves x. Notice I would get minus 5 halves, so that's minus 2.5. And then if I added 1 to that, that would actually leave me with negative 3 halves, or negative 1.5. So either one of these forms is totally acceptable. Okay, but I like the point slope form only because it's so much easier to create. Well, now let's go ahead and see how we might be able to extend this question. What I'm going to be interested in doing here is to take a look at, can I find a formula for the slope of a line, again, still that's going to be secant to the curve, but maybe it starts at the point 1, 1, but I don't really tell you what the other point is going to be. So I kind of make this point locked in, 1, 1, but the other point, let's just suppose it has mystery coordinates. The best that I could tell you is that whatever the x coordinate is, I know that I will find the y coordinate by taking x and squaring it, right? That's how you get y. So that's why instead of writing x comma y, I wrote x comma x squared. Okay, now let's go ahead and do this, and let's assume that we're not going to choose the same point. We're not going to do 1 and 1, 1 again. That would be silly. So let's go ahead and actually see. Notice here, all I'm looking for is the slope, so I'm just going to try to compute m. All right, so my m value would just be, well, let's see, I'll take y coordinate minus y coordinate over x coordinate minus x. There it is, done. Now, I can see here that I could probably simplify this formula a little bit, right? Because the numerator here can be simplified by factoring it and then canceling it out with the x minus 1 that's in my denominator. And so really what I have here is x plus 1 is a nice formula for my slope. Again, this is assuming that x is not a 1 to begin with. Otherwise, I would still have a problem from the beginning. And you can even see that this formula is perfectly valid for finding the slope, and it worked up here, right? Notice if I plugged in the value 1.5 in for x, that would have told me the slope between these 2 points. 1.5 plus 1 is 2.5, and that's exactly what we had right here. So what I have now is a way to kind of quickly grab the slope at all times. So if I want to do 1, 1 and 2, 4, easy. Just plug in 2. The slope is 3, right? Immediately I can compute this. But the interesting thing now is I could say, what would I conjecture is the slope of the equation of the tangent line to the curve at the point 1, 1? Well, notice in the picture, something interesting here can begin to happen. My tangent line is going to be sitting right here. And so what I kind of want is that it seems like if I could move this secondary point with the mystery coordinates, if I could slowly start to kind of move that towards the value of 1, my red line might slowly begin to line up with my blue line. We'll see how that works in some more examples in a second. But I kind of almost want to find the slope of the line when I'm using the point 1, 1, and I guess the point 1, 1 again. Well, if I was then making a guess, I could then say that, well, we would guess that m would be equal to, and I guess that would be, if I'm going to use the other point as 1, 1, that would say m is maybe 2, like it's 1 plus 1. I'll put a question mark back there, like I'm not really sure. And so the equation of my tangent line would then be equal to something like this, right? Notice I'm using 1, 1, but also the slope of 2, right? So I would get something that looks like y equals 2x, and I guess minus 1 I should have there if I put it in point slope form, or slope intercept form. So this is kind of strange, but this is actually where this idea of a limit comes in to help us. Let's take a look. What we're going to be interested in doing is applying a limit to help us find our slope. We're going to be interested in seeing what happens as this particular secondary point slides towards our primary point here of 1, 1. To help try to illustrate this further, take a look at what happens in a picture, something kind of like the following. Here I have a black function, okay, and I have a point with a tangent line on it. You can see this blue tangent line. And you can see here, kind of like what we did in our previous picture, we have 2 points, a P and a Q, where I'm creating a secant line. And what we're talking about here is thinking about what begins to happen as I slowly begin to slide this point Q towards the point of P. Now, watch what happens to the slope of the red line. The slope of my red line is slowly going to be kind of starting to line up with the slope of the blue line. It's not doing it quickly, but it's slowly getting there. Notice how close the points P and Q are, right? Look how close they are to each other. But as I continue to slide the point Q closer and closer and closer and closer and closer to the point of P, can you see how the red slope is almost becoming exactly the blue slope? Now, we have an idea already in play that describes one thing moving towards another, and that is the idea of a limit. This is where, on the next definition, we can see this concept coming into play. The tangent line to the curve y equals f of x at a specific point is going to be a line that has the following slope. And notice that again, our slope here is going to be found by applying a limit. Now, you'll notice right away that if I was to just kind of ignore this limit right now, we can see that this portion right here is calculating the slope of a red line. If I have a fixed point A and a mystery point X, this is how I would calculate slope, right? This is exactly what we did right here. We did slope formula by just doing our mystery points minus our original points, doing the change in y over the change in x. That's all we have here, change in y over change in x. But to turn it into a tangent line slope, we will say, let's take the value of x, let's take that starting x coordinate and slowly push it back towards the value of a. Just like what we were doing over here. We were taking the value over here and slowly moving it back this way. And you can see that's kind of what I have here in this picture, is we're taking that value of x, and notice up here, we're pushing it towards the value of a. And as we do this, as x gets really close to a, look how close they are, the slopes of these lines are almost going to match. So that's what we're shooting for. And so that's where this first definition comes from. Now there's another definition that we could use, and it's actually just going to be the case that by just relabeling some of the stuff in our picture, we can get to the second definition, which is actually going to be the definition that's a bit more useful for us. We'll see here that instead of labeling this point as a and this point as x, why don't we label the first point as a and the second point as a plus some gap h. So we're going to kind of be calling this distance in between these two things h. You can kind of see it down here. And if we were to do that, then notice that the formula that we would end up with when we do change in the y's over change in the x's is actually going to look like this. This formula here is still, without the limit, going to be the slope formula. Notice again, change in y's given right by this, and the change in my x coordinates, if I do a plus h minus a, is just h. And so when I now have my limit, my goal now, instead of pushing this point x towards a, I just want to say I want this gap between these 2 points to slowly disappear. I want h, the size of the gap, to slowly become 0. So this is really cool. What this is allowing us to do is to actually say, if I only know one point on the function, can I still find the slope of the tangent line? And with the power of a limit, we are actually able to do this. This is a concept that you really may want to go back and continually review, and it's really helpful to try to imagine this moving picture of one value slowly sliding towards another. And so these red lines and blue lines are starting to line up perfectly.